Okay, we're starting with integrals of polynomials. And first thing we're going to do is we're going to talk about Riemann sums. So the reason why we have Riemann sums is because back in the day, before they figured out integration, which is basically the second part of calculus, the B part of calculus, before they came up with that, they were like, okay, well, how do we approximate the area under the curve of a function? And the only way that they knew how to do it, and the way that you guys did it back in elementary and middle school, was to make little boxes or little rectangles and then count up all the boxes and add them all up together. So that's called a Riemann sum. There's three types of Riemann sum: a left sum, a right sum, and a midpoint sum. And then there's another way to approximate the area under the curve, which is the trapezoid sum. So we're going to do all four using this function right here. So this is an approximation of the area under the curve. Here's the function that I'm giving you right now, x minus 2 squared plus 8. And just to make it fit on the graph, I forgot to make it a negative, so add in a negative right here. So it should be negative x squared, or x minus 2 squared plus 8. Okay, it's asking us to find the area under the curve on the interval 1 to 5 with 4 subintervals. So first I need to figure out what's the width of basically every rectangle that I'm going to take. Well, to figure out the width, I have to find my delta x, which is b minus a over n. So we take the end of the interval that we want minus the beginning of the interval that we want over the number of intervals. So I want 4 subintervals, so I'm going to divide by 4. 5 minus 1 over 4 is 4 over 4, which is 1. So basically every delta x that I'm going is going to be in an increment of 1. Well, that's easy on for this problem, but sometimes it's not so easy. So it goes 1, add an increment of 1, so 1 plus 1 is 2, 2 plus 1 is 3, and then 4, and then 5. Okay? You can figure these out pretty easily. Just plug 1 into the original problem, get 7. Plug 2 into the original problem and get 8. Plug 3 into the original problem and get 7. 4, 4, 5, negative 1. Oops, negative 1. But if you can't figure it out, or if it's harder and maybe you have trig functions in there, you might need to go to y equals, plug in your function, and then go to second table set, and then I'm going to start it at 1, and then this is my delta x. I want increments of 1, and then you can keep auto for both of those. So now when you go to your table, it's all set up for you. 1, 7, 2, 8, 3, 7, 4, 4, 5, negative 1, which is what we have right here. All right? So what we're going to do for the left sum is we are going to draw rectangles starting from the left and moving right. Let's plot these points first. So 1, 7, 2, 8, 3, 7, 4, 4, 5, negative 1. Okay. And then if I plug 0 in, I'm going to get 4. So we'll just plot that anyways. So here's our graph. All right. So there's our graph. For a left sum, I'm going to draw rectangles starting from the left-hand side. Remember, we're only starting at 1. So I'm going to go to the point at 1, draw straight down, and then the rectangle comes straight across from here. So this rectangle is going to be, my base is 1, so 1 times 7, because my height is 7. All right, for the next rectangle, I'm going to have a height of 8, and go left and go straight down. And so that's 1 times 8. This one, my point is on 7, so it's 1 times 7. And then this point is at 4, so it's 1 times 4. So the area that I'm actually finding is this whole shaded region right here. Which is a little bit more than what we want. Probably if I did smaller rectangles, I'd get a more accurate area approximation. But for now, that's what we're going to have. So you can either write the left sum as 1 times 7 plus 1 times 8 plus 1 times 7 plus 1 times 4. Or you can write it as 1 times 7 plus 8 plus 7 plus 4, because the interval is the same. The base is the same for all of these. Sometimes, though, they'll give you a table where the base is not the same, and so you'll have to do it this way. You can't make one giant delta x for that base. So if the bases are all the same, though, you can leave the 1 on the outside and then add up all the ones on the inside. Okay, so that answer is 26. All right, let's do the right Riemann sum now. So same points. I'm going to draw my curve. And then I'm going to do a right Riemann sum. So for the right Riemann sum, I'm going to start from the right hand side and move over. So from 5 over here. That's going to be weird. It's going to be 1 times -1. And then my interval for this one, notice that it's under the x-axis, and when it's under the x-axis, it's going to be a negative number. So this is going to be 1 times 4. This one coming from the right will be 1 times 7. Going this way, and then I stopped at 1, so it's 1 times 8, and then that's it. So my right Riemann sum is totally different from my left Riemann sum. This adds up this area in this area, and this one. And then I have this area right here. Okay, so my right Riemann sum will be 1 times 8 plus 1 times 7 plus 1 times 4 plus 1 times -1. Or, since my intervals are all the same, 1 times 8 plus 7 plus 4 plus -1. Is 18. Okay. All right, notice for the left sum, you do the interval, which is 1 times 7. So for the left sum, you use 7, 8, 7, and 4. 7, 8, 7, 4. And then for the right sum, you're going to use -1, 4, 7, and 8. So you're coming in from the right. So I do the interval times -1, 4, 7, and 8. So the right sum, you use the last 4 terms. For the left sum, you use the first 4 terms. Okay, midpoint sum is a little different. We still plot the same points, 4, 4, 7, 8, 7, 4, and -1. Okay, let me this up a little bit. Okay, so for the midpoint sum, we are going to go to the middle of this point and figure out what that is. And then for the midpoint for this one, I need to go right in the middle in between. And for this one, I need to figure out all the middles. So right here, actually I don't need this one right here, but I do need 1.5. I need to figure out what value it is at 1.5, at 2.5, at 3.5, at 4.5 to do a midpoint sum. Let me go back up to my table right here, and I'm going to put in values like 1.5, 2.5, 3.5, and 4.5 right in the middle. I'm going to change my table from my delta x to 1.5, or just 0.5. Okay. So at 1.5, I'm at 7.75. At 2.5, I'm at 7.75. At 3.5, I'm at 5.75. And at 4.5, I'm at 1.75. So, back to here. Right here at 1, I am at 7.75, right in between. So there's my rectangle. You draw straight across and straight down. This one's going to be 1 times 7.75. And this one is also at 7.75, at 2.5. 1 times 7.75. At 3.5, you're at 5.75. So it's 1 times 5.75. And at 4.5, you are at 1.75. So we are 1 times 1.75 for this area. Okay, so for a midpoint sum, it looks like we're getting a little bit more accurate. We find the area of all that, the area of this region, and of this region. Okay? So, my midpoint sum will be 1 times 7.75 plus 1 times 7.75 plus 1 times 5.75 plus 1 times 1.75. You don't have to write it like this. If all the intervals are the same, then you can just do 1 times 7.75 plus 7.75 plus 5.75 plus 1.75. Okay? All right, that's for midpoint sum. And that's a little bit more accurate, like I said before. Now let's check the trapezoid sum. So what happens is you end up making a trapezoid with all the points. So here's 4, 7, 8, 7, 4, negative 1. Okay. So on this interval, from 1 to 2, we make a trapezoid right here. And here's our trapezoid, base like this, and there's our trapezoid. Well, the area of a trapezoid is 1/2 base times height, right? So we're going to do 1/2. The base is 1 right here, That's the base. And then the height 1 and the height 2. So height 1 is 7 plus height 2 is 8. So it's 1/2 times the base and then times the first height times the second height. We'll do the trapezoid for this one, which is 1/2 times base of 1. Height 1 is 8. Height 2 is 7. This one, it's from 3 to 4. It's 1/2 times 1, base of 1. Height 1 is 7. Height 2 is 4. And from 4 to 5, here's our trapezoid from here to here. It's going to be 1/2 times 1 times height is 4. Height of the other one is -1. So trapezoid sum will be 1/2, all of this, 1/2 times 7 plus 8 times 1 plus 1/2 times 1 times 8 plus 7 plus 1/2 times 1 times 7 plus 4 plus 1/2 times 1 times 4 minus 1. If you notice, this 7 and the 8, this 8 right here is used twice, this 7 here is used twice, this 4 is used twice. So a trapezoid sum you can approximate by 1/2 times the delta x, and then you can do the first one, 7 plus, and then 2 times every middle one, plus 2 times 7 plus 2 times 4, and then the last one. And so if you double all the middle terms, you include the first one and the last one, and you 1/2 and 1/2 out in front. That's also the trapezoid sum. Okay? So the trapezoid sum is also, if you want to write this down, this one is the average of the left and right sums. So you can also just figure out the left Riemann sum and the right Riemann sum and then average the two. But I would like you to know this. I would like you to know this formula, and I would also like you to know how to calculate it if the intervals aren't the same, which is this way, because you're going to need to know how to do all three. Okay? So the left Riemann sum, to recap, the left Riemann sum will use the left 4 terms. The right Riemann sum will use the right 4 terms. The midpoint Riemann sum, you're going to have to use the middle. And then the trapezoid, you use 1/2, and you do the first one, double all the middle ones, add them together, and then the last one. Okay? So why don't you, on your own, try this one. So pause this video, try it, and then come back and see if you get the same answers that I got. Okay? Okay, my delta x is 2. I've got intervals of 2 already set up, and it gives me this. Now, if you don't have this correct intervals here, you're going to have to do the delta x each time you do it. So for left sum, right sum, midpoint, and trapezoid, you want to have your delta x for each rectangle. But if it's the same, you can put the 2 on the outside. I'm going to do it both ways just so that you see. So on the interval 0 to 2, the base is 2. I'm going to use the left value 1. And then on the interval 2 to 4, base is 2. Use the left value of 3. 4 to 6, the base is 2. Use the left value of 4.3. 6 to 8, the base is 2. Use the left value of 5.4. 8 to 10, base is 2. Use the left value of 6.3. Or you do 2 times 1 plus 3 plus 4.3 plus 5.4 plus 6.3. Okay. For the right sum, we do 2 times. So from 0 to 2, I'm going to use the right value, which is 3. From 2 to 4, base is 2, use the right value of 4.3. Base is 2, use the right value of 5.4. 2, use the right value of 6.3. 2, use the right value of 7. Okay, or you can do 2 times 3 plus 4.3 plus 5.4 plus 6.3 plus 7. Okay, midpoint sum. I can't really do it using 5 rectangles, but what you would need is you would need values from 0, you would need 1, you would need 3, you would need 5, you would need 7, and you would need 9 in order to do this. So, but I don't have those values, so we're going to skip midpoint for this one. But that's what you would need. You would need the values at 1, 3, 5, 7, and 9. I can do trapezoid though. Trapezoid, we either do 1/2 times the base is 2, times 1 plus 3 plus 1/2 times the base is 2, times 3 plus 4.3, and then you keep going. Or you do 1/2 times the base times the first number, 1, double all the middle ones, plus just the last one. So you double all the middles, you keep the first and the last the same. So that's trapezoid sum. Alright, the sum can also be written with sigma notation. The sigma, this is just sigma, and it adds up all of the rectangles that you calculated, the area of the rectangles. This is the base. These are the heights. F of x1 is the height at x1. F of x2 is the height at x2. F of xn is the height at xn. And then what we really want is the area under the curve. Now, if we make the number of rectangles infinity, like if I have an infinite number of rectangles, then I'm going to get the actual area under the curve. We use limit as x goes to infinity because we want an infinite number of rectangles. The more rectangles you have, the more accurate your area. Just take a look at the problem on the other page. We only had 4 rectangles here to estimate the area, but look how more accurate it would be if I had like 15 or 20 rectangles. So the more rectangles you have, the more accurate your area is going to be. Okay? Now, you're going to have an overestimate. You're going to overestimate the area. And then you're also going to underestimate the area sometimes. When you overestimate the area, let's talk about if you have an increasing function. If you have an increasing function, then a left Riemann sum is going to underestimate. Left Riemann sum, underestimate. A right Riemann sum will do the opposite. It will overestimate, because just look at this graph. So if we're increasing, and if I did a right Riemann sum, I'm coming in from the right. That's an overestimate. Now it's exact backwards for decreasing functions. And this is how you're going to justify, if you want to justify, is is your approximation an overestimate or an underestimate? You're going to say, well, it's an underestimate because the function is increasing, or it's an overestimate because the function is decreasing. So for a left Riemann sum, a decreasing function will overestimate. And a right Riemann sum will underestimate. Okay. Decreasing, a right Riemann sum. You have all this extra area that you didn't accomplish. Okay? And then there's two more, concave up and concave down. For concave up and concave down, midpoint will underestimate and trapezoid will overestimate. And for concave down, it's the opposite. Midpoint will overestimate and trapezoid will underestimate. Okay, so that's Riemann sums. Do the Riemann sums homework, and if you have any questions, you can ask me during class. Thanks. Bye.